Well, this is it, the third video on elements in the periodic table and what they're good for. And we've looked at smartphones, we've looked at how metals from the S block are used for organometallic chemistry, and just those two, magnesium and lithium, were used for such. The other S blocks are kind of more for the inorganic chemistry side, using water, things like that. And then we looked at the D block, or the transition metals, and how they can be used for doing carbon-to-carbon coupling. And if you don't remember anything else, remember that this kind of chemistry of making carbon-carbon bonds is very tough. And transition metals, they whistle and, I guess, sing as they do it. They're just amazing in their ability to coordinate carbons to each other and do it very rapidly to make polymers, to make chiral compounds. They're just really cool, I guess, agents for change, those transition metals. I need to move on, and I need to cover just, I guess, three things. We need to look at oxidation states and coordination compounds. I've been using this term ligands. We need to kind of define that a little bit. And then last, I won't spend too much time, look at the P block elements. Maybe just focusing in on oxygen, carbon, and some of the halogens. Before we get there, though, I thought this would be fun. Maybe not. It looks like a mess here. But we're going to just walk you through this, and I'm going to go down a level for this. So what we can do to determine oxidation states as we go is kind of look at where the electrons are. So if you don't mind, I'm using skeletal structure. So what we have here is a carbon, another carbon, another carbon. So there's four, 1, 2, 3, 4, and this is called a butane chain. CH3, CH2, CH2, and then there's CH2. So there's two hydrogens at this carbon. But I've drawn this bond in red here to kind of say these electrons, though they're not owned by the bromine, if you're counting oxidation states, the bromine being more electronegative, or I guess so not necessarily more electronegative, but the electrons by polarizability kind of cheat towards the bromine. So we sort of treat those as bromines, electrons, because they're cheating that way. Now, to make the organolithium that we talked about, we said that halogens connected to carbons are very, very important bonds. We use them all the time in organic chemistry, carbon to chlorine, carbon to bromine, not so much to fluorines. Well, we can take two equivalents of lithium solid. And what would the oxidation state, if you remember from, I guess, first semester general chemistry or high school chemistry, if you have an elemental form of something, the oxidation state for that is 0, since it's an elemental form. So if we take that, and we know lithium likes to gain an electron or lose an electron. Hope you're saying lose an electron. It's got one electron. It loves to lose. That's why we use it in batteries. It's a lot of potential as you take that electron and, I guess, not necessarily pull it away, he pushes it away. A lot of energy there that we can use. So let's say he gives up his electrons. There's two of them. So we're going to make one of these with a positive charge, and he's going to give one electron to this carbon, because remember, if bromine walks away, he walks away with these electrons that are in red. He walks away with those two also. So we're going to have two of these lithiums, and we're going to consider their electrons as kind of blue. Those two electrons are given to this carbon, and the two lithiums are split. One goes to the carbanion, we call this butyl lithium. That's how we make our organolithium reagents. The other one is lithium chloride, and if we have the right solvent, by the Chatelier's principle, we could precipitate that out and just have a really nice reaction to our butyl lithium. All right, hope that first line kind of makes sense. And now what would the oxidation state of lithium be here? We're just going to track lithium and any metals as their oxidation state goes. It wouldn't be 0 anymore, it'd be the charge. It would be +1. So I'll put that in quotes up here, +1. So it went from 0 to +1 as an oxidation state. Now let's go ahead and move on down to the next reaction. We're going to go all the way down to here. And what we're going to do is take two of these. I've abbreviated them as just BU as butyl, and Li. So we kind of made it a little simpler to deal with. We're going to take two of those, and we're going to react it with copper bromide. Now, being it's a transition metal, this bond might be a little more covalent, not so much ionic as lithium chloride, because this is a far left meets far right, non-metal meets very left metal, so very ionic. This might have a little more covalency. Remember how we said copper's more towards the right, its electronegativity is going to be a little bit higher than lithium, and there might be a little bit more covalent bond. But either way, bromine still cheats. Those electrons, we'll say, are really more his than the copper's. So it has a negative charge, and because this has to be neutral, the copper has to have a plus charge. So what would the oxidation state of this copper be? I hope you're saying it would be not 0, but like lithium, it kind of follows the charge. It would be +1. Now, an interesting thing to kind of just as a sort of side consideration is to consider what electron was taken. Now, if you remember the electron configuration, I flipped it here because we're going to go charge, is usually 4s and then 3d. But we're going to go ahead and say, remember, with copper, you're all the way near the very end of the D block, so you've kind of filled up most of the D. Now, in the textbooks, in the neutral copper structure, you would say we have 2 here and 1 here, but we know that in your knowledge of electron configuration for copper, we always take and put 1 electron, so we completely fill up the 3d and leave the 4s half filled. Why? Because it does happen over time that the 3d slips below the 4s level. That's why you had that sort of 4s1, 3d10 for copper, the element. Now, if we're taking 1 electron to make it positive charge, there it goes. It's coming right out of that 4s. So we'd say the electron configuration for the copper would be just 3d completely filled, and we'd have 10 electrons. All right, back onto the main track of getting this to react with 2 of these butyl lithiums. How would that reaction look? Well, copper, remember, can make more of a covalent bond than ionic, kind of a mix. And so these butyls are going to say, look, I'm better off finding someone who's closer in electronegativity, see a lithium. I can get a little more covalent bonding between the copper and me. So they're going to start gathering around the copper. So I put 2 of them. Now they're bringing their own electrons. This kind of BYOE, bring your own electrons. These 2 are owned by the butyl group. These butyl group here and this one here brought their own electrons. So we didn't add anything to copper. He didn't have to pull out any electrons to use for bonding. And the bromide, it's kicked off to bond with 1 of those lithiums, and the other lithium with a positive charge balances out this di-coordinated, I guess, we call this a cuprate. The di-alkyl cuprates, this would be a di-butyl cuprate. And if you look at the charge then, we didn't change his oxidation state. It's a +1 charge, +1 oxidation state, or 1 oxidation state. The charge of these butyl groups was negative. Well, 2 negatives with 1 positive makes 1 collective negative. So they sometimes will write this without these charges, and they'll just write the whole thing as 1 negative. So I don't want to confuse you. I'm going to get rid of these, or at least cross them out. And you'll sometimes see cuprates written like with a little bracket. This whole thing has a negative, and it's coupled with a lithium positive charge. All right, so the oxidation state of the copper did not change from here to here. Now I've drawn a little treasure chest because in the next reaction, we're going to have an oxidative addition of our butyl bromide to our dialkyl or dibutyl cuprate. Let me take a pause because this is kind of taxing on the brain. So remember, his oxidation state right now is +1. But we're going to see he's going to have electrons leave from him, they're in green here, and go to the butyl group that's right here. I'm going to explain that. We said these bromines connected to a butyl group tend to take their own electrons away from this carbon. Well, the carbon then, when he has to bond to this copper, he ain't going to stay positive. He's too electronegative for that. He's going to rip those 2 green electrons from the copper and put him in a new oxidation state. So what would that oxidation state be if you can kind of consider these 2 electrons as having been taken from copper and given to this butyl group? It's the one that's really coming in. It's the new one. These 2 are already present. The bromide here his in red, he brought to the party, what would the oxidation state be here? And I'll put a little question mark there and let you think on this for a while. He's going from a +1. He's lost 2 electrons to this butyl group, so I'm hoping you're saying it would be a +3. This copper, that's why they call this oxidative addition. Oxidative addition of the butyl bromide, going from a linear to a tetracoordinated copper. That's why they call it oxidative addition, because the copper is being oxidized. But don't worry, he's going to go back to kind of a reductive elimination. This reaction is going to be a reductive elimination, and I'm going to finish up here. And if your brain's hurting, I can understand. This is a big mess. But I hope each of the steps, if you want to review the video, kind of makes sense. So what we do here is we're going to give these green electrons back to the copper, but in an indirect way. So this butyl group, this is the power of your metals. They can connect a butyl to a butyl to make, basically, octane. These 2 electrons in blue are going to be used to bond to this butyl group, because you can't have 4 electrons in a bond. So he's going to bring the 2. He accepts the 2, you might say. And I know it doesn't happen that way, but just for easy accounting, we'll say these go back to the copper. Well, then the bromide walks away with his own electrons. They're all in red. And it walks away with the lithium, and we leave just this part of the structure behind. Well, we know the butyl group here is negatively charged. So guess what the charge we get back is just +1. And guess what the oxidation state is? It is just +1. That's the journey you take to make and use your dialkyl cuprates. You can use them to make some really cool carbon-carbon bonds. That's the, if I put an eyeball on it. Wow. Wow. All right, that is a mess. Hope that kind of makes sense. I'm going to stop the video there, and because that's a story and it's long enough. We'll finish off as we go into, I guess, the rest of the notes. It was going to be 3 videos. No, it's going to be 4. How do we find oxidation states? How do we look at and understand coordination compounds? We've talked about it a little bit, and then move on to just the group 4 and 5A and 6A elements from the non-metals. Bye-bye.